You are welcome once again. Today we'll be looking at linear regression. By way of introduction, the term regression is a historical anomaly. It was coined by Francis Galton in the 19th century to describe a biological phenomenon. The phenomenon it described was that the height of descendants of tall ancestors tend to regress down towards a normal average. The phenomenon is called regression towards the mean. It simply means that the average value of y is a function of x. That is changing with x, changes with x. Y here is described as the dependent variable. So the average value changes with changes in x, the independent variable. As a way of historical background, the word regression sounds like go back in some ways. The term has appeared in early writings since the late 13th century and is derived from the Latin word regressus, which means a return. It is used in different fields with different meaning, but in any case, it's always referred to as action of regressing. In philosophy, regression is used to indicate the inverse logical procedure with respect to that of the normal apodictic, that is demonstrable or indisputable truth, in which we proceed from general to the particular. Whereas in reality, in regression, we go back from the particular to general, or from effect to cause, or from condition to the condition. That is, sometimes you want to know what are the factors responsible for a particular thing. So that is the conditioned. So you try to look at what condition it. For example, if blood sugar is a dependent variable depending on a lot of factors. So the blood sugar is the conditioned, is the effect. So from the blood sugar, I want to know what are the factors that are conditioned to be like that, or what are the causes. So that is why we say move from particular to general, or from effect to cause, or from condition, the conditioned to the condition. Still continue on the historical perspective. In statistics, the term regression has an ancient origin and a very special meaning. The man who coined this term was a certain Francis Galton, was a geneticist. He was more than that. He was a philosopher also. He was a geographer. He was a psychologist. You know, he dabbled into many things. In 1889, he published an article in which he demonstrated how every characteristic of an individual is inherited by their offspring, but on an average to a lesser degree. So, for example, children with tall parents are also tall, but on an average, their height will be comparatively less than that of their parents. So, this phenomenon also physically discussed as regression, that is returning. Since then, this term has lived on to define statistical technique that analyze relationship between two or more variables. So in Galton's words, this corresponded to the concept of regression towards mediocrity, and the name of the statistical analysis techniques. Regression, look at Galton, was a cousin to Charles Darwin. And he actually took part, contributed to the development of genetics. He was the one that coined the word nature and nurture. He said that nature is what you acquire, you got from your birth. Nurture is other influence apart from what you got at birth. Now, Galton universal regression law was confirmed by Carl Pearson. Carl Pearson was the person that first described chi-square, was regarded as the father of mathematical statistics, and he also described the Pearson correlation coefficient, though it was said that Galton was the first to use the word correlation. Yes. Carl Pearson was Galton's student. So he collected more than 1,000 heights of members of family groups. He found that the average height of the children from a group of short parents was greater than the average height of their father's group. Average height of children from a group of tall fathers was lower than the average height of their parents. So that is, if parents are extremely tall, the children will be tall, but they will be shorter than the parents. If parents are extremely short, the children will be short, but they will be taller than their parents. That means that they tend to go back to what is normal in the society, in the population. So if their parents go to the extreme, some attribute, there's a tendency, you still see it in the children, but they will try to move back to the common, to the average in the population. That is regression towards the mean, to the average, or they call it then regression towards mediocrity. That is, the height of the tall and short children were regressing towards the average height of all people. So I think we are through with the historical perspective. Let's look quickly at what regression means now. A way of predicting an outcome variable from predictor variable. As we have said before, you move from known or from condition to the condition. That is, from a particularity to the cause, from effect to cause. What are those factors? You know, we call them predictors. So when the predictor or the factor or explanatory variable is one, that type of process is called simple regression. Since in regression, the outcome variable is always one, only one variable, only one variable. But the exposure, the predictor variable, may be more than one. So when the outcome variable, of course, is one, the predictor variable is only one. That is simple regression. It's a form of bivariate analysis in the sense that there are two variables involved, the outcome and one exposure. But when we have more than one exposure, more than one predictor, so the regression will be multiple regression, which some people call multivariate analysis. They wrongly call it because it's actually multivariable analysis. Multiple regression is multivariable analysis. But many people call it multivariate analysis, even many experts, or even in some book you will see. But if you actually go through a standard statistic textbook, you see they are called multivariable analysis because it's always one outcome. Then you can have many exposure, many predictors. Those ones that are actually multivariate analysis, they have many outcome, many exposure. That is, the outcome variable is usually more than one. Example are factor analysis, multi-dimensional scaling, multivariate analysis of variant, what they call maneuver. In those cases, there are more than one outcome you can calculate at the same time, apart from the fact that there are many exposures. Those are the ones that are called multivariate analysis. But people call multiple regression multivariate analysis, well, whichever way. We can predict any data using the following equation. You know, statistics try to model life situation. That is, what goes on in real life. Trying to model it with equation, with graph, with table, so that people can conceptualize. Just like when people want to build cathedral. They, in order to have a mental picture of what they want to, so that many people that will contribute money may carry the same picture as the convener, maybe the pastor who has the vision. He didn't know that they will not be able to force people to bring money out to realize the vision unless they create the model for people to see. So they now build small miniaturized form of the cathedral or the church or whatever building, and now be showing it to people every Sunday. Then people begin to bring money. So that is modeling. So what statistic does is to model through situation. And how, in regression, from what we have just said, we are trying to look for, move from effect and say, what are the causes of this thing? So in order to actually get the causes, you just have to build a model. And the model, the way you build it is either you use an equation or a graph, a picture or equation. And that is what has happened here. So in regression, building a model, what you're interested in, you are moving from the outcome, then you now build a model. But of course, in trying to predict the outcome, because this outcome, this model, the outcome is the dependent variable. The model, there will be either one or many independent variables, which are the predictors, will be in the model. But of course, those predictors may not be able to 100% predict the outcome. Whatever different will be the error. So let's just move on. Just like the example I gave about church also, by the time people build, contribute money, they now build it. It's possible by the time they finish building, what they build may not be exactly as what they saw. So maybe the model was not able to predict completely what the drill that they were showing that was not able to predict exactly how the church will be when they finish building. So the difference is the error. Now, the simplest description of a relationship between two continuous variables, because in regression, most of the advancement in statistics start with continuous variable you can quantify, whereas it's later that intelligent people also try to now adapt the same thing to maybe categorical variable, or the variable that don't necessarily follow the same pattern as the original one. The same thing with correlation we just finished discussing, though the people to first describe correlation started with Pearson correlation, which is for continuous variable. But later, the other intelligent people also now adapted the concept to also suit variables that are now continuous. It's the same thing with regression. And that is why we first of all discussed linear regression. Later we discussed logistic regression, which is an adaptation of linear regression. So the simplest description of relationship between two continuous variables is a straight line. Now, the shape and position, if you remember when we talk about correlation, it talk about the linear relationship actually. That is, it has to do with quantitative variable. Even if when you even adapt correlation to variables that are not naturally quantitative, but their number will still be there, like an ordinal variable. You just have to score because it has to do with number. So the same thing here, when we are talking of relationship between continuous variables, we are saying that, okay, as one increases, what is the value of this? Or as one decreases in value, what is the value of this? So the simplest way to do that is to use linear relationship. Of course, there are other deviations from that. We'll talk about that later. The shape and position of a straight line is defined by two things: the intercept and slope. So this concept was actually borrowed from mathematics. Of course, statistics is a branch of mathematics, but most of the people that develop statistics over here were not mathematicians. They were professionals in other fields that are actually needed, especially in the field of biology and social science. So biologists and social scientists develop statistics for many years, and they borrow from mathematics. Like this equation of a straight line is the concept in mathematics, and that is why I'm first of all describing equation of a straight line. The intercept is the value of y when x is greater. Look at the example of a straight line. Draw a straight line is try to look at the relationship between two variables here. The variable on the horizontal axis and the variable on the y-axis. And by convention, when we are talking about relationship between two variables in which we believe one depends on the other, there is one dependent variable and there is one that is independent. So the independent determines the dependent. The dependent is determined by the independent. For example, if we talk about salt intake and blood pressure, blood pressure cannot determine salt intake. It's in salt intake that will determine blood pressure. So whenever you are looking at two relationship variables, if there's any cause effect or one depends on the other, you must be able to know which one depends on which one. So by convention, the y is regarded as the dependent variable, while the x is the independent variable which determine y. So, and the y is usually plotted as vertical and the s as horizontal by convention. So when you look at relationship now, when you now look at as y increases, s increases. So you see the way it slants up. Of course, it can slant down also. In that case, telling you as y increases, s decreases. We'll talk about that later, about the slope. But what I just wanted to see here is that there is a relationship, this straight line, which means that one increase, the other one increase also. But the way the line is not always from the zero origin. It's not always from origin. If you cross the graph, apart from passing through where x and y meet, which is the origin, 0. So two things now. There is a slope in the sense that the graph is slanted. If the line is vertical, it's undefined. If it is horizontal, the slope is 0. There is nothing change. That shows that y, even when s is changing, y is the same thing. So there's no relationship between them. But since it's slanted or slanting, either downward or upward. So that shows that as x increases, y also increase. You can calculate the slope. That is change in this vertical line over change in this horizontal line. That will be slope. That's one thing, one characteristic of the line, the straight line. The second is, since it didn't start from the origin, it crosses y-axis. It eventually crosses x and y-axis, but the intercept of interest here is where it crosses y-axis. That is the intercept of interest, that is y-intercept. And if you look at it, when it touches y-axis, it means that if you trace back to the origin, the value of s is 0. So that is the intercept, the y-intercept correspond to y, the value of outcome variable, which is the y, when x is 0. That is, when that particular thing you think is the independent variable, the predictor that is causing y, if nothing changed there, y still has its own value. So that shows that it's not everything about y that is caused by that x. So how y has value when x is 0, or when nothing happened about x. So apart from the fact that it may not be only x, there are many other, so that it is a pointer that if you have 1, 2, 3 x, that is independent variable, everything, they may not be the only contributor. But as you're going to see, you can, through analysis, regression analysis, you can identify the major contributor to the extent that if you give recommendation, you'll be able to solve the problem to a certain extent. Now, those two things are the slope and the intercept that define a straight line. So the slope is change in the y, is the gradient, or they call it how slanty it is in ordinary language. If it's very slanty, that shows that per unit change in x, y, which is the outcome variable, change very well. But if it is not so slanty, slopy, that shows that per unit change in x, y just change small. If it is horizontal, there's no change in y, even when x is changing. That is what it means. And the intercept is what the value of y when x is equal to 0. And writing it, look at the equation of the straight line, y is equal to mx plus c. This is the convention in mathematics. But in the next slide, we show the convention in statistics. This is not the convention in statistics. This is convention in mathematics. Equation of a straight line, y is equal to mx plus c. C is the intercept. M is the gradient, which is the slope. So once you know the slope, and which is the gradient m, and know the intercept, so if somebody supply you the value of x, you can calculate y, you can predict y. Once you know the gradient and you know the intercept, so just let somebody give you the value of the predictor, you can tell the value of the y, which is the dependent variable. Now, before we talk about how we relate directly, how it concerns statistics and concerns you, let's still explore the concept of the slope and the gradient very well. Can you see? This was telling you the type of slope you can have, though I discussed that initially. Please, if you have your question, you can be typing. Now, you will see that this one is slant up. Now, when we are talking of the direction, I know when you are plotting graph, the positive direction is towards the right, left to right. So if you start from the origin is 0 where x and y cross, as is cross. If you move toward the left of x, that is negative direction. You move towards right, is positive. For the y-axis, if you move up, that's positive. If you move down, that is negative. Now, when the graph slants up from left to right, that is positive slope. Now, when it slants down from left to right, that is negative slope. Let's look at it. Second. When it is just horizontal, the slope is 0. So in that case, you can't say it's positive or negative, it's 0. When it's vertical, it's undefined. It's not defined. It's not defining anything because by convention, the x is the independent variable. Y is the dependent variable. So this is 0 is defined that is 0 in the sense that along the horizontal as s move, the y is constant. But this one, what this one is saying that as y is changing, x is constant, but it doesn't concern you because that's not what you're looking. That's why it says it's undefined. Because by convention, the y is the outcome variable and x is the predictor. So what you are interested in is when s changes, how much of y changes. So but this one is telling you that y is changing, s is constant. So they are not constant. So that should we can say that there's no relationship between both of them also anyway, if there's no change. Just like this one, these two, 0 and undefined, there's no relationship between them. Because if one is changing, the other one is standing. For both of them. Here for the 0, x is changing, y is constant. For this vertical line, y is changing, x is constant. So no relationship between them. But these positive slope and negative slope are the one that define the relationship. Now, we still move further so that we still explain the slope versus the intercept. So what slope and intercept actually mean? The slope we have already said can be, it shows the shape because actually what the slope is saying is telling you the shape of the either is the graph slant up or down. Then the intercept, so the shape, if it's slant up, it's positive slope. If it's slant down, it's negative slope. Now, the intercept talk about the location of the graph in geometric space. It can be positive or negative. Look at it now. This fourth graph now, the two graph above, you can see positive slope, both of them. But the first one, the intercept is positive. The second one, the intercept is negative. No, I already said this y-axis above 0 is positive direction, below 0 is negative. So the intercept is where the graph crosses y-axis. Here, it crosses y-axis at the positive side. Can you see above 0? So the intercept is positive. Here, the second one, it crosses y-axis as the negative side below 0. So the intercept is negative. Even though for both graphs, the slope is positive for both of them, but the intercept is positive here and the intercept is negative here. The same way when you come down to the two lower graph, the slope, you can see the slope is negative for both of them, because it's slant down. But the first one also here, the intercept is positive. This one, the intercept is negative. Can you see now? So you can have 3, 4. The 4 combination of them is that this one is positive slope, positive intercept. Positive slope, negative intercept. Negative slope, positive intercept. Negative slope, negative intercept. So you see, the slope talk about the shape, the intercept talk about the location in geometric. When you say location, can you see all those ones that are intercept positive, they are above. Can you see? Some are above. Why intercept negative? Some are below. So let's continue. Now, adapting this to statistics now. So the same graph, instead of calling, if you remember the equation of the straight line in mathematics is y is equal to ms plus c or c plus ms. Here you say, instead of saying c, intercept, c, you call it a. It's the same thing, just the nomenclature, you call it a. The statistics call it a, which is the intercept. Or we call it constant. Constant, that is why mathematics call it c, because it's constant. It's constant. That is, even when the independent variable is not changing, the dependent variable still has a value which is constant. That's why mathematics call it c, constant. So we call it a here. The regression, the slope, which is m there, is b here, which is change in y divided by change in x. That is in further math, that's what we call dy ds. Now, slope of the graph is the regression coefficient. That gradient is called regression coefficient. It is regarded as the change in y per unit change x. If you say y depend on x, whenever x change by 1, how much change in y? That's what it does to you, for you. That's the gradient. So once you know that, by the time you know that, you know the constant, all you need to know is for you to say, okay, what is value of x? You know that it's equal to a plus bx. A, multiply that x by the change in y per unit change in x to really know what is changing, plus the constant, you give it the value of y. So the constant is the value of y dependent variable when x independent variable is 0. You have said it. Each value of y is equal to a plus bx, and this is the regression equation. Y is equal to a plus bx, or say bx plus a. Doesn't matter. Now, the regression equation. So you have the one we just demonstrated on a simple form is for, we just assume that the one we just use, okay, there's one independent variable. You can adapt the equation for simple regression in a situation where only one exposure variable or predictor variable, or more than one, that is multiple. When you have, that's how you have B1, B2. But this BO, in writing equation, that A, which is the constant, you don't call it A, you just call it BO. It's a coefficient also, but B0. Because when you are running with the software, the software also bring it as coefficient. There is the coefficient for the constant, that is for the intercept. So B0 is the intercept, and B1 x1 mean this is B1 mean the regression coefficient, the slope for the variable x1. So for simple regression, you don't even need to put 1, but you need to put 1 because this to differentiate from B0. But for multiple regression, B0 is there, B1 x1, B2 x2, as many, even if they are up to 10 like that. So why we just say Pn xn mean up to, if it is up to 9, as many variables you have. So can you see simple linear regression equation, multiple linear regression? You see, we are going to see the way it comes out in graph also, even though we have looked at the way the straight line is, but this is the equation. So as I've said, the model is either equation or graph, still doing the same thing. Now, in the scatter plot in which we have a fitted straight line in the cloud of points now, in the situation where you just have the many points scattered, you now have a straight line. In order to model the relationship between the attributes, the location of each point on the graph can be expressed as a function of that line by saying, okay, y is equal to a plus bs plus e. You know, if you look at this equation now, you just say y, this is the constant plus bx. Now, here is introduces something that is not there, error. Now, if you remember, when I first of all brought, I said you can model by say outcome plus model plus error, because the model, the BO plus BYX, that is the equation, the model you have built. But the model may not 100% predict what you are predicting. In that situation, there may remain whatever it cannot predict will be the error. So that is why you write the model like this. The other one is equation. But here, if you actually want to write the model, you write it like this. This is for linear, this is for multiple, just like what we have seen. So maybe when you see the picture. So now, if you, by the time you actually plot the graph, that's where all of them will not be on a straight line, to be sincere. You see something like this, where the line is drawn along. So you discover that not all the points, most of the points will not even be on the line, like the data point. And this point you are seeing is where for each person, each participant, where the value of x horizontal meets the y. So where they meet, that's where their point is. But this line, you see that not all of them are on the line. Now, how do we draw it? How do we actually draw it? The method of obtaining in a situation where you just have scatter, what is the best line? Like these two graphs I just show you now, just show you. If I'm to print it out or give it to individual, all of us to draw the right line, we are going to draw different things. Our line cannot be exactly the same. We cannot draw, because people try to, okay, let me draw the line that will fit everything, will close to everything. So somehow, if you use hand to draw, everybody will draw slightly different thing. Now, what is that is using manual method. But the line, the method that will give us, whether we use it by use hand or whatever, the line that will give us the best will be the line that is closest to all of them. You know, all of them cannot be on the left line, but when you draw the line, when you now measure averagely the distance of each point from the line, when you square it and add it together, the value will be the smallest. That is, for example, now, all of us in this class now, if we are to draw the line, if we draw the line, we now, for each person, the line you draw, you now look at measure the distance of each point from this line. For all the points, you now square the distance and add everything together. The person that gives us the smallest value will be the best line, because that line try to give you is the closest averagely to all the points. You begin to say, why should you need to square before you add? You know, when you draw the line, some value will be below the line. That is negative deviation. Some will be above the line. That's positive. And we are adding positive and negative. If you just say you neglect the value, you are committing mathematical offense. So the best is to, when you square it, negative value become positive. So when you draw a line, many people draw many lines, and you try to square the deviation of each point from the line and square it. When we add it together, the line that gives us will be the line of least square. That's the best fit. It's the one that best fits it, and is line of least square. So that's why they call that method of least square. Method of least square just means that the method that will minimize the distance between the line and all the points averagely. That is method of least square. Of course, the computer will do it for you. Now, this method of least square, now the logic behind it is that, let's say after we have drawn it now like this, you see that there are two, once you draw the line, there are two values for each of the point. The observed value and the value, if you draw a perpendicular line from that observed value to the line, that particular point where the perpendicular line from each value join the line, that would be the predicted value, because that is the predicted value by the line for the point. That's what the line predicts for the point. So you now see a difference between the predicted value of y and the observed value of y. The observed value of y is actually what you observe in your study, what is there. But the predicted is what the point that is represented on the graph for that particular value. So the difference between that is the error, or the residual. That is, you know, where each point, if you draw a perpendicular line to the line, where they join the line, that's what, that point where they join the line, that's what the line predicts for each of them. But the actual value is what you are seeing. So the difference now is the error or the residual. That is, the line is trying to, the regression line is trying to predict, but it has done its best. But it now remains the accuracy, the difference in what it predicted and the actual value is the error. Now, in simple linear regression now, look at it. You can see iron that, okay, change in y all over change in x, a unit change in x. That is the slope. That's the B1. The intercept is where it crosses the y-axis, which is the P0. Can you see? Now, in real life, if we want to even calculate this thing in real life, how do you calculate? Because all you need actually is the B1, the regression coefficient, and the constant, which is the B0, the intercept. Now, let's look at the way you can compute the regression coefficient and the constant, the A, B, and A. Changes dependent variable is measured by covariance of x and y. That is, if you actually want to look at, okay, the change in y due to x is measured by covariance, is change, that is both of them, how they vary together. While change in the independent variable, which is x, is measured by the variance. We know that the variability in x, which is x minus x bar, which is x minus mean of x square divided by the degree of freedom, which is the variance. So the changes in x is measured by the variance. If those are the way the changes in y also is measured by the variance of y. Look at, that's what I first put here. Variance of x is this, s minus s bar square all over n minus 1. Variance, you can be written in this way also. Instead of say s minus s bar square, you say s minus s bar minus s minus s bar. No, that is that into, so you multiply instead of square, you write it 2 times. It's another way, just for you to conceptualize. The same thing with the y. This is the variance of y. But the covariance of y and x will be this. Covariance will be x minus s bar, y minus y bar all over the degree of freedom. Can you see? You see, this first one is variance of x, this variance of y. The covariance of x and y is this. So x vary on its own, y vary on its own. They have their variance, how they change. But the portion that they change together, the changing together will be their covariance. And if you consider this, change in x is the variance of x, yes. Change in the y is the variance of y. Change in y due to change in x is the covariance of x and y. And the regression coefficient, as we have defined, is the change in y per unit change in x. That is, change in y divided by change in x. So therefore, the regression coefficient B will be covariance of x and y over variance of y, of x rather. So if you now put this is the covariance, so it will be this all over divided by this is variance of x. If you divide it by this, if you come here and say you change the division to times, the numerator will become denominator. This n minus 1 cancel n minus 1. It will now be this all over this. This is the regression coefficient. So it's just a slightly like different from correlation coefficient. Now it can be written in this form also, but it's just one mathematical manipulation that brings it gives the results fast. But just for you to conceptualize, this is the, and once you know the B now, all you need to do is y. Since y is equal to a plus bx, then mean of y is equal to a plus mean of bx, b and mean of x. So you can substitute. Once we know B now, all you need to do is calculate the mean of x and y to be able to get a substitute for this number. We have an example here. Just quickly look at it to stop today. Look, this is looking at the height and the pulmonary dead space, height of children, 15 children, and their pulmonary dead space. Now, for you to calculate the regression, how from here now you know that the x is the height of the children, the pulmonary dead space is the dependent variable. It depends on the height. Height cannot depend on pulmonary dead space. The pulmonary dead space is a part of the respiratory tract that is not involved in the exchange of CO2, exchange of oxygen and CO2 during respiration. So that is the dead space. So the pulmonary dead space now depends on the height of the child. So if you now look at the way we compute it, all you need to do is the element. If you remember the formula, all you need is mean of x, mean of y, and that's all. So, and multiplication of the x minus s bar. So you calculated you have already known the mean is here, down here. So if you remove mean, x minus s bar, remove the mean from each x, it gives you this. Remove mean of y, which is the pulmonary dead space, from each value, it gives you this. So when you multiply these two, it gives you this. Then if you square, because you want to know the variance of x, if you square x minus s bar, it gives you this. So the regression coefficient will be this summation of this sigma over summation of this 5426.6 over 5251.6. That's it. It gives you. So the regression coefficient 1.033. So once you have known that now, y, which is the constant, which is the intercept will be, y is equal to bar y, that is mean of y minus b mean of x. So when you just bring it, you know mean of y is this, mean of x is this, multiplied by the b, it gives you this. This is the intercept. Therefore, the equation for the regression will be y minus 82.4 plus 1. So you can write in this way and say 1033x minus 82.4. It doesn't really mean which one you move. I think we stop here. We stop here. By maybe on Tuesday, we'll talk about how do you know, after you have fitted the line, how do you assess the goodness of fit of the line? That's where all this R square and F ratio comes in. In a simple way, I think you're able to conceptualize how you can predict value of Y from X. So let's stop for question. Any question? Any question? Is there any?
Good evening, sir.
Good evening.
Good evening, sir.
Good evening.
Good evening, sir. How are you, sir? Thank you very much. Okay. Wonderful session. Please, I just want to confirm that A, you know, that last slide that you showed us, that A equals to Y minus BX. The A is the constant, the Y is the dependent, the B is the regression, and the X is the independent.
Yes. Yes.
Okay. So you were just trying to get the constant, so that way you cannot use it to calculate for other. But once you have the constant and once you have the regression, you cannot calculate for the other one. Okay. Yeah. Thank you.
Thank you. Somebody is asking questions. Say, if one independent variable is measured many times, repeated measure, can multiple variable regression be used instead of simple regression? Well, if you measure the thing many times, in that case now, it is believed that because there are factors that are involved, so each of them is different variable. Yes, it's multiple. Each of them is different variable. So what you take at a particular time is different from what you take at another time, because it's possible some factors come into play. So both of them are repeated. They're actually different factors. If you remember in ANOVA, repeated measure is a form of factorial ANOVA also. In that case, that shows that you are introducing another factor. So it's a form of, if you have to use that, it will be a multiple regression. Any other one? Any other one? Can you hear me? Hello?
It's clear. We are fine. We can hear you. It's fine.
Okay. We can hear you. We can hear you. Okay. Any other question? That show is very clear. If you cannot ask, if you don't want to ask, you can shout it. Because that show that is very clear if you don't have question. Okay, that would be great. I want you to be clear. It's not that I want you to be confused or anyway. So that would be great if you don't have question. Okay. Yeah, okay, if there's no question, let me just pause the recording.